Hello viewers, today we are discussing calculation on isotopes. In our previous lesson, we worked on isotopes and isobars. We were made to understand that an isotope is simply a phenomenon whereby two or more atoms of a given element has the same atomic number but varying or changing atomic masses due to the change in neutron number. And we also made to understand that isobar is the complete opposite of what an isotope is because for an isobar, we have the same atomic masses for different atoms of element, but varying atomic numbers. So if you have not seen that very lesson, please, I would love you to go ahead and see that very lesson. It will help you to understand what we're about to take right now 100%. So today we're going to be looking at calculations on isotopes. So here's the first question on it. Chlorine has two isotopes, chlorine 35 and chlorine 37, with relative abundance or percentage abundance of 75% for chlorine 35 and 25% for chlorine 37 respectively. Calculate the average relative atomic mass of chlorine. Now don't forget, in our previous lesson we were made to understand that when we talk about relative abundance, we're talking about the rate or the proportion of the existence of a given atom of a given element in nature. So for the fact that we have two atoms of this element, we're talking about the same element chlorine, but for chlorine 35, we have more chlorine 35 in nature. We have 75% of chlorine 35, a lot of chlorine 35 in nature, compared to chlorine 37, which is just 25%. That's what we call relative abundance. Relative abundance is simply how much of a given atom of an element we have in nature. Now, how do we get the relative atomic mass unit for this very given element chlorine using the relative abundance? Don't forget, a formula was given in our previous lesson, and that's why you have to go to that previous lesson. So for us to get the relative, most times we'll call it average relative. For us to get the relative atomic mass for a given element, so what we have to do is simply this. It's very, very simple. We just have to get the summation, which is sigma, we call it sigma, summation of the partial atomic mass unit, or the partial relative atomic mass unit of isotopes, of each of the isotopes given to us. Now we can see we are given two different isotopes, chlorine 35 and chlorine 37, and we are given their percentage of existence in nature. So for us to get the relative atomic mass of chlorine, what we just have to do is to get the partial atomic mass of each of those isotopes. Now, how do we get the partial atomic mass of each of those isotopes? Don't forget, by the time we get the partial atomic mass, then we add them up. So how do we get that? This is how we get the partial atomic mass. That's going to be the summation. Let's see how we get the partial atomic mass. So that's going to be isotope abundance. Isotope abundance, that's what it is, over 100 times the relative atomic mass of each isotope given to us, over 1. This is how we do it. This is how we solve for the partial atomic mass of isotopes. This is how we really solve for it. So by the time we get the isotope abundance is just like 75. Look at this. Chlorine 35 is 75% in nature. So isotope abundance over 100 times the relative atomic mass of that very given isotope. So by the time we get each of the partial atomic mass for each isotopes, by the time we're done with them, we add up everything. That's how we get the relative atomic mass unit for a given atom of an element. So let's quickly get that for chlorine 35. So for chlorine 35, it's going to be 75 over 100 times 35 over 1. That is isotope abundance over 100 times relative atomic mass of the isotope. So by the time we do that, then we sum it up. The next one is 25 over 100 times chlorine 37 over 1. Now this helps us to get the relative atomic mass of a given element to a very high degree. So we're going to be using our calculator. Let's quickly punch in the figure to help us quickly get this. There's no time. 75 times 35 divided by 100. That will give us 26.25. Here we have 26.25. Plus then the next is 25 times 37 divided by 100. You have 9.25. Yes, 9.25. So together, 26.25 plus 9.25, what do we have? we have 35.50 atomic mass unit. This is the atomic mass unit for chlorine, as simple as ABC. Example 2, an element has two naturally occurring isotopes. Now look at the elements. The first isotope has an atomic mass unit of 9, and the second isotope has an atomic mass unit of 10. That's an element Q. If the relative atomic mass of the element Q is 9.68, determine the isotope abundance of each isotope. Now don't forget, we have to get the percentage portion of each of those isotopes in nature. Now look at, as you can see, we are given the atomic mass unit of each of those isotopes. Now the first isotope for this element Q has an atomic mass unit of 9. The second isotope for this same element Q has an atomic mass unit of 10. So now don't forget, based on the formula up there, now for us to get the relative or the average relative atomic mass unit of this very given element Q, we will need to get the partial atomic mass unit of each of those isotopes given, as you can see up there. Now by the time we get the partial atomic mass unit of each of them, we sum them up to get the relative atomic mass unit of the element Q. But as you can see, we've been given the relative atomic mass unit of this very given element, but we are not given the percentage abundance of this given isotopes. So what we have to do now, we are going to do something. We're going to use our mathematics and skill. Now the very first element is Q. As you can see, is 9 right here. Second element has an atomic mass unit of 10. Now each of this atomic mass unit for each of these isotopes has their own percentage abundance, their own percentage of existence in nature, but we are not given. So let's assume that the very first element, the very first isotope, I beg your pardon, has X%. And don't forget, by the time you add this and this together, we're going to get 100%. So this has X%. So if this has X% and we just have two isotopes, so it means the other one must have 100 minus X%. More or less like saying this is 30% in nature. Then if this is 30%, for example, here it's going to be 70%. So if here is X%, then here is 100 minus X%. So we're going to use each of them, to get our partial atomic mass unit for each of the isotopes, just like what we have up there. So by the time we get our partial atomic mass unit, then we can sum them up. And by the time we sum them up, we're going to end up getting 9.68, which is a relative atomic mass unit. That's the first step. So let's get that done right away. Let's get the partial atomic mass unit for each of them. That'll be X over 100 times 9 over 1. By the time we do this, you're going to get our partial atomic mass unit. Then the next 100 minus X over 100, then times, what do we have? Times 10. That's what we have there. So by the time we do this, what do we get next? 9 times X is 9X over 100 plus then 10, open your bracket, 100 minus X over 100. I don't want to take it off. By the time I simplify this, I want something easy. That's why I don't want to simplify this. Now equals to 9.68. That's what we have. So we're going to get the LCM. So this 9x over 100 plus 10, open bracket 10 minus x over 100 equal to 9.68. So what's the LCM of 100, 101? That's going to be 100. You know that. So that's our LCM is 100. So 100 and 100 is 1. 1 times this is 9x. Plus 100 divides 100 is 1. So 1 times this is to give us 10, open your bracket. 100 minus x. So 1 and 100 is 100. 100 times 9.68 give us 968. So you're going to write out the top. That's 9x plus 10, open your bracket, 100 minus x, close it up. So 968. So there's 9x plus 10 times 100 is 1000. 10 times x is minus 10x equals to 968. So it's high time we got our like things collected. So that's 9x minus 10x. 9x minus 10x. We'll send this to the other side. 968 minus 1000. So 9x minus 10x is minus x equals to 968 minus 100 will give us minus 32. So the minus sticks are minus. So x is 32. So that's what our x is. Now, since we've gotten our x as 32, don't forget the very element, this very element with atomic mass unit of 9, this isotope, is the x, while the other one is 100 minus x. So that means the other one, this is 32% in nature, while the other one, which is 100 minus x, will be 100 minus 32, which is 68% in nature. So as simple as A, B, C. So there's also another method we could use. We could use another method. This is an alternative method. This is another way to get it done. Now, this is how we can also go about it. By the time we have the first isotope, 9, the second isotope, 10, we could assume, since we have the atomic mass unit, the RAM to be 9.68. We know that already. So we can assume that this should be X percent, while this should be Y percent. This is going to lead us to simultaneous operation. Whichever way you want to approach it, you're going to get the same result. So if this is X percent, now it's high time we got our partial atomic mass unit for each of the isotopes. So let's get that done now. So that's X over 100 times 9. Now since we want to get this, we're going to get the summation of the two of them. So Y over 100 times 10 over 1. So by the time we add them together, we end up with 9.68. So 9 times x is 9x over 100 plus 10 times y is 10y over 100 equals to 9.68. So the next thing we are going to do, we're going to collect our like terms. We're going to find our LCM, sorry, I beg your pardon. So that's 100 stays right here. So 100 divides 100 is 1. 1 times 9x will give us 9x. 100 divides 100 is 1. 1 times 10y will give us 10y. 1 and 100 is 100. 100 times 9.68 is 968. So right here we have our first equation, 9x plus 10y equal to 968, equation 1. Now, how do we get the second equation? And don't forget, this is x percent and this is y percent. So it simply means by the time we add x percent and y percent together, we're going to get 100%. So if x percent plus y percent gives us 100%, so what we're going to end up with is x plus y equals to 100. X percent, which is x over 100, plus y percent, y over 100 equal to 100%, which is 100 over 100, which is 1. So by the time you do the mathematics, you know what you're going to get. So we're going to end up with x plus y as 100. So quickly, what do we do? The next thing we do now, we're going to solve it simultaneously. We're going to use our elimination method. That's the best method to use. So we're going to agree on where to eliminate. Let's eliminate the y. So we're going to look for a way to get the coefficient of those two of them. We're going to look for a way to get them become equal so that we can get them eliminated. So if this is 10, this is 1. We can times here by 1. Then why we multiply here by 10. 1 times this is 9x. 1 times this is 10y. 1 times 968 is 968. 10 times x is 10x. 10 times y is 10y. 10 times 100 is 1000. Now, how do we do it? For us to eliminate this, they are the same signs. We have to use our minus. So 9x minus 10x will give us minus x. 10y minus 10y, they take out each other. They're eliminated. So 968 minus 1000 will give us minus 32. So minus takes up minus. What do we do next? So x is 32. So if x is 32, fix it here in equation 2. So x plus y is 100. X is 32 plus y is 100. So y is 100 minus 32. We're almost there. So y is 68. So x is 32%, y is 68%. As simple as ABC. Okay, guys, there's a final example for today's lesson on calculation on isotopes. So there's a final example. Now here's a question. A sample of an element V exists in the ratio 1 to 5. Calculate the partial atomic mass unit of each isotope if the relative atomic mass of the element is 36. We have to calculate the partial atomic mass unit. Partial atomic mass unit of each isotope. Now don't forget, there's a big difference. I want us to really clarify a couple of things. It's a difference between the mass of a given isotope, when we talk about the mass, the relative mass of a given isotope, and the partial atomic mass of that same isotope. Now, if you look at the two examples we've worked on so far today, now we are often given the mass of a given isotope and the percentage abundance of that isotope. Now, with the percentage abundance, we get the partial atomic mass of that isotope, which will add up to other partial atomic mass of other isotopes. That will give us our relative atomic mass of that very given element. So it's very important for you to note the difference between the partial atomic mass of a given isotope and the exact atomic mass of that given isotope. The partial atomic mass is gotten after we've used the percentage abundance given with the atomic mass of that very given isotope. But right here, we've been given the relative atomic mass of the element, and we are given the percentage. I'll call this I can call this the percentage abundance, and also I can call this the ratio of the partial atomic mass of the isotopes. So don't forget, say a sample of an element B exists in this ratio. So you should get the partial atomic mass. So we've been given the partial atomic mass in a way via the ratio given to us. So we're going to assume this. We all understand mathematics. That's what we're going to use. Now, if the RAM of this very element is 36, we have to get the partial atomic mass, whereby we've been given the same partial atomic mass via the ratio. So what's it going to be? First, we're going to get the total ratio, which is 1 plus 5. 1 plus 5 is 6. So for the very first partial atomic mass, now there's some books you check, you will not see them use the term partial atomic mass. They'll just use the term get the atomic mass of the isotopes. So I want to note that they're talking about the partial atomic mass in this very case. So 1 plus 5 is 6. So what's it going to be? That'll be 1 over 6. Since the total atomic mass is 36, 1 over 6 times 36 over 1. 6 here 1, 6 here 6. So the very first partial atomic mass, for the very first isotope is 6. So the next is going to be 5 over 6 times 36 over 1. 6 here 1, 6 here 6. 6 times 5 is 30. So this 2 here are the two partial atomic mass of the two various isotopes for this very given element V. So we are not asked to get the atomic mass of this very element V itself. We're just asked to get the partial atomic mass unit. So as simple as that, very easy and direct. So that's everything, the final example. So the next we're going to look at now is the take-home. Okay, pals, it's high time we got ourselves tested with these take-homes to see how much we've gotten from today's lesson. So here are the questions for today's take-home. Boron exists as an isotope mixture containing 80% of boron 9, 15% of boron 10, and 50% of boron 11. Calculate the relative atomic mass of boron. As simple as that. That question is simple and very direct. The next question, an element Y exists in 3 isotopes form in the ratio 2, 3 to 4 if the isotopes have their atomic masses as 29, 30, and 31 respectively. Solve for the relative atomic mass of each of element Y, I beg your pardon. Solve for the relative atomic mass of element Y. Now the very last question, an element B has 2 isotopes, that's B6 and B7. If the relative atomic mass of B is 6.1, find the isotopic abundance or the isotope abundance of each of the isotopes. All those questions are very simple and direct. I'll love you to solve each of them. By the time you're done solving them, I'd love you to leave your answer for me in the comment section to tell how much you've gotten from today's lesson. So at this very point in time, we're drawing the curtain on today's lesson. If you found this lesson resourceful, please subscribe to this very channel and share this lesson with others. See you in the next exposition. Thanks.